I'm pleased to be joined today by Victor Lee. Victor is head of product strategy and developer relations at TigerGraph. He holds a PhD in computer science from Kent State University and a master's in electrical engineering from Stanford University. He is also a prolific author and co-author of numerous research papers on the challenges and possibilities that data brings us. And Victor will be talking today on laying an analytics foundation for the enterprise. Victor, please take it away.
Hi, I'm Victor Lee, head of product strategy at TigerGraph, and I'm excited today to talk to you about laying an analytics foundation for the enterprise with machine learning and graph databases. So I'll just get to my slide presentation and we'll get started. So our agenda for today is first, talk about what do you need for the next generation analytics foundation? And that will lead me to a consideration of using a graph and of course, machine learning. And then I'll show you three basic approaches for graph and machine learning with use case examples. First, unsupervised learning with graph algorithms, then feature enrichment from graph features, and third, in database machine learning. So today you have so many considerations for trying to set up your analytics foundation for the future. How do you decide among them? You hear AI and machine learning for the analytics, of course. You say it's got to be in the cloud, it's got to be scalable, it's got to be explainable. And some people are saying it should be data-driven or outcome-driven and or user-driven. So which of these matters? Well, I'm going to suggest that the first thing is it should be data-driven. And because data is your source for all analytics. You can't get good results if you don't start with good data. When we say data-driven, we're usually talking about your strategies and your actions should be driven by the data, but they're really talking about the analysis results when they say that. So in order to get to your analysis, you have to start with good data. Next, let's say it should be scalable, because whether you have a lot of data today, you're going to have a lot more data tomorrow. Your compute needs will grow. Your data is going to grow, whether it naturally grows organically or because you see that you can and should be working harder to get results. And third, this may be less obvious, but I'm going to say it should be connected. And the reason for this is simple, that analytics is about seeing the relationship between things. Basic statistics, your simplest statistics, or just making a simple bar chart. It's seeing how one factor relates to another. So how things connect, how they relate is essential. And what you need to do today is bring all your resources together, all your data together, connect it from that larger foundation. Then you can start to do your analytics, and by marshaling all your data together in the right way and representing it with connections, that is how you will set up the foundation for your next generation analytics. Gartner's recognized this. Gartner has said graph analysis is possibly the single most effective competitive differentiator for organizations. If you're pursuing a data-driven operation and decisions, that is, you have to start with data and you have to start with connections, and that means graph. At the recent Graph+AI Summit conference, 3 industry leaders all made their comments about why for them, graph and the combination of graph with AI and machine learning was essential. Harry Powell from Jaguar Land Rover commented that when COVID-19 hit, that all their forecasts went out the window. They had to start over and understand this new reality. The way to understand that reality was to use graph analysis. Noel Johanna from Forrester Research says, algorithms get all the praise, but actually it's about the data. And Dr. J.U. from Intuit probably handles more than half the financial information for more than half the people in the United States through their tax preparation and small business accounting software. We need knowledge graphs to make the right connections. The knowledge graphs for AI do the matchmaking. They reveal the deeper true realities. And so each one of them says graphs are essential. graphs fundamentally make AI and machine learning better. We all know we should be doing machine learning, but you want to start from the right place. You want to start from a graph. So, in case you need a refresher, what is a graph? It's a set of nodes like customer, order, product, and the connections between them, sometimes called edges. So, and these edges can have names and types which reflect their meaning. So this enables you to connect all your things. The connections themselves are data. So you're actually, in some sense, producing richer, denser, more meaningful data. With the same amount of data, it means more because those connections have meaning. It also is the natural way to connect your different data sets, breaking down your traditional silos. Why do they need to be in separate systems? Connect them all in one graph. You still run your applications in different subsets, but some analyses will now be able to look at all of the data. Of course, there are security features to take care of that. Modern graph databases have all that access, privilege, control so that you can decide who gets to see what. But once you have all that data, you can ask deeper and smarter questions. You can look for the semantic patterns of relationships, and you can search far and wide. Graphs, if you know any graph theory, you probably heard the terms breadth first search and depth first search. The fact that we're even talking about breadth and depth indicates that graphs inherently let you search far and wide. Next, you have more computational options. You have all the computational analytical techniques you had before with traditional tabular data. On top of that, you have graph algorithms and graph-enhanced machine learning. And lastly, as we'll show you later, you can get explainable results. Some of the modern techniques, deep learning, are great. They produce wonderful, exciting models, but they're a little obscure. They're often unable to explain why they made that decision. In a lot of cases, you need a little bit more confidence, either for your own organization or because you are responsible to explaining to a regulatory agency or a compliance organization why you made your decision, or even telling your customer why you made that decision. So the semantics of graphs allow you to model your data in a more semantic way and produce explainable results. Quickly, 3 real-world examples: healthcare recommendations. One of the largest health insurance companies in the US has assembled a graph brain of 1.3 terabytes, and they use this for real-time care recommendations, producing better healthcare at lower cost. Secondly, we mentioned Jaguar Land Rover. They're using this industrial supply chain, a smarter, deeper supply chain, to produce analytics for decisions to plan their manufacturing, to take care of disturbances like the massive disturbance of COVID-19, to better meet their customers' needs, to make better strategic decisions. They initially thought they would save $25 million. They now think they can save $100 million a year. And finally, financial services. We mentioned organizations like Intuit. There are also banks that are using graph for real-time fraud detection. It shows them, it enables them to do their customer 360, their know your customer, which they do for their own needs and for regulatory needs, and to detect fraud and detect anti-money laundering in an explainable way. So I mentioned there are 3 different ways that we can use graph and machine learning or advanced analytics. Number 1 is to use analytical queries and graph algorithms. Computer scientists have come up with graph algorithms, some of them dating back over 100 years. And these were originally for academic purposes. Some of the very early ones were actually motivated by real world applications. And that's what we're seeing today. We have banks coming to us asking us, can you do a scalable community detection? Can you do a scalable page rank? Because they're using that for their fraud detection. So, and some of these, like clustering, if you studied machine learning, you know that one of the classic applications for unsupervised learning is clustering. Well, there's graph-based clustering. There's also ranking, deciding which is the most important or which is the most centrally located. Centrality is very important for business planning, for trying to optimize things like your marketing campaigns. Where do you focus your attention to have the most influence? Find out who is most influential in the network. Similarity, so recommendation is based on similarity. People who liked this also bought that. If you find one interesting case that you can market to, or there's a problem that needs to be fixed, look for all the similar cases. Again, graph analysis gives you a richer, deeper understanding of similarity. And lastly, just finding out, here's my data, what is happening in my data? Doing that open-ended analysis of frequent pattern discovery. These are all graph algorithm techniques, and they're all valuable for real business applications. Taking a little bit deeper look at that healthcare recommendation, say we have a network of patients and healthcare providers, and there are both generalists and specialists among the providers, and we want to find out who is the most influential specialist in that network. And why do we want to do that? Well, there are a couple reasons. Maybe it's to improve better healthcare. Maybe you are a medical supply or pharmaceutical company that wants to know who should you focus your marketing attention on. So it could be to improve the healthcare. It could be to improve business. Use PageRank. PageRank is inherently designed to find out the most influential entity among a self-referential group. Providers are making recommendations or referrals to other providers, the one that they not just point the most to, but important doctors look to this person. So if you're just not an ordinary doctor, but you yourself are already an influential doctor, but you look to this person for even better care, that makes that person really important. And that's what PageRank does. Who was influenced by these leaders? Then we do some community detection, because we say, who are they influencing? So the combination of two graph algorithms provide this very important real world analysis. Could be for healthcare, could be for any number of things. Second, another example, I mentioned similarity analysis, where when you find one interesting case, you want to find the other cases like that. This chart here, it's a patient journey. So you've got the horizontal axis showing time, and you've got the vertical axis showing different types of encounters with the medical and healthcare system. And we're sort of showing the patient's journey over time. And there are a couple things that are red flagged, and those are cause of concern. And in this case, it means we should have somebody reach out to that patient, give them a phone call, send them an email saying, I think you really need to come in and see the doctor, or we're concerned that you're not taking your medication, or something like that, to provide better health care and prevent more serious consequences down the road. This was discovered by looking at this patient, and maybe they did finally talk to the doctor and we were able to improve their health. You want to find the other people like that. So you model this situation as a graph. And the way you do that is, for each person, you have the different events or attributes as other nodes. So the person is a node, and these different features, again, it could be a diagnosis, it could be every little encounter they have with the healthcare system is another feature. And then there's scores to indicate, could be the recency, the strength of how many times this happened. There are different ways you can assign weights, but what you end up with is a weighted vector or a weighted list of scores. You now look for other people that have similar lists with similar weights. You can use a formula like cosine similarity to give that a score, and people that have high cosine similarity scores are very similar to that patient. We have major businesses that are using this very real technique. A third example, HBO, Warner Media, integrated, several businesses, Warner, HBO, AT&T, they spun off Xandr as an advertising arm. And as you know today, advertising is all about analytics. And so they have this massive identity graph, but because they've got data coming from multiple sources, they sometimes have the same person with different digital identities. And this creates what we call the entity resolution challenge. We have a person in the data set who is represented multiple times. How do we actually figure out that that's the same person? You know, they've got some overlapping information, some that's different. So it's not a perfect match. Is that in fact the same person or not? And this can happen not only because you have multiple sources, but just multiple events. Over time, people move. Sometimes data entry, there are typos. So there be these minor mismatches. So, but the reason why you want to know, is it the same person? Because that same person is going to have, there's only one real person, one set of financial circumstances, one set of interests. And for banking in particular, we talked about, you know, media and entertainment recommendation, but now the banking industry needs to do the same thing. They have a requirement called KYC, know your customer, and they have to understand who is the real person behind this account. Whether, because, you know, all sorts of malfeasance, various types of fraud are based on the idea of setting up false identities. And they have to try to do the investigation to try to figure out who is the real person or who's the real beneficiary. Sometimes you have so-called, you know, shell or corporations, holding companies, but who is ultimately benefiting from that? And they need to figure that out to do good business, to do good compliance, to be good citizens. So this entity resolution is really important. Here is how it's done computationally, or at least one of the ways it's done computationally. You have all these different digital identities. And then using something like cosine similarity or some other similarity algorithm, you assign a score. So, and you do this across the graph, maybe the whole graph, maybe just some subset of interest, but you come up with a score between each pair of vertices. And you can see that some of these scores are higher than others. And then what we can do is a clustering and basically put the ones that have high scores together and the ones that have, you know, lower scores, they'll be separate. So what we ended up with was these 7 different digital identities we resolved into 2 physical persons, Barry Markin and Beryl Markham. Oops, skip to page. So that is all just using graph algorithms. That's one technique. A second technique is to do graph feature extraction. If you know, the word feature is used in machine learning to represent a property, just some attribute that has a score, usually a real valued score, and you build a list of these features. And so you end up, as I mentioned, with the cosine similarity, a list of scores. But this, you apply much more advanced techniques, not just cosine similarity, but you do your machine learning, your deep learning. But this is the data preparation. You have to prepare the data before you send it down the line into your machine learning algorithm. So, example, China Mobile used this graph technique for real-time phone call classification. They had, over the years, identified 3 types of unwanted calls, and they wanted to provide their customers with real-time alerts. You have American phone companies who are doing the same thing now, where I know Verizon does this, where on your phone, you will see an alert if this is a suspicious caller. Well, this is one way that that is done. They form a giant phone call graph. Each phone number is a node, and each phone call is an edge. And you can see that they're clearly going to have millions of phone numbers and billions of these phone call edges. And China Mobile took a 2-month slice, a rolling window of the 2 months most recent calls. You can see the size, the statistics are over here of how big a graph that was. But the key thing was they did graph feature extraction. What they did was, let's look at the graph and map out some basic patterns of caller behavior. And for example, this pattern number 1 is just, if caller 1 calls 2, how often does call 2 call back? Does that, over a certain time window, does that happen a lot or not? So you can produce a score. Stable group, do you call a certain set of people regularly over time? Now, one, you could it's pretty easy to do that with tabular data. Two, it's a little bit harder because now you have a group of people you're concerned about. Three, long-term phone call. Again, it was the duration of the phone call. That would be easy to do with tabular. But four, many in-group connections. So this is like building on that stable group. I call these people fairly regularly, and then they call themselves. So that's community detection. That's definitely a graph problem. And number five, three-step or four-step friend relationship. One calls two, two calls 11, 11 calls three, and three calls one again, or one calls three. So they form a loop. Again, that would be tricky, possible, but very computationally slow in tabular data. With a graph, very efficient. So they did over 100 of these features, 100 features, put it into the machine learning system. They were able to successfully, in real time, detect 3 different types of unwanted calls, produce 3 different types of alerts. The thing I want to point out is that these 118 features actually get extracted every time the phone rings. Somebody makes a phone call, it extracts the 118 features in real time to see how do we score that caller. And based on this, the score of that caller, what the model says, the model prediction, then you get alerted, is this a good or bad person? Because that behavior changes over time. Somebody that was okay today, suddenly tomorrow we decide that's a spammer. Using these very explainable features. When I was talking about these graph features, they make sense, right? If you train your model based on them, if you use a decision tree method, then that explainability is maintained in the result. When that model detection, when you get a score, when you get a prediction, should I answer this phone call or not? In theory, it could give you the list of scores and says, we're telling you that this is a suspicious caller because of these features. If you use deep learning, you're not going to be able to do that. But graph enables you to do that. And third, talking about deep learning, well, we're not against deep learning. It's great. It's producing wonderful things, but you can use it with graph also. So you build your graph, and then you do feature enrichment, like we mentioned. And then the next step is you have your choice of techniques. In the China Mobile case, they used a decision tree, but you could use there are any number of graph neural network techniques or non-graph. The thing about this feature extraction we did here, we put all these scores on each phone, and those phones are the nodes in the graph. So all the properties of interest are on the nodes. So while the edges were important during the analysis, during the preparation phase, for the machine learning phase, if we choose to, we don't have to use the edges. So we just pay attention to the nodes. That is tabular matrix data. And so all your traditional techniques can be used. And the exciting thing about some platforms like TigerGraph, because they're scalable, because they're very analytical and algorithmic in their nature, you can do those algorithms right in the graph. You never have to, the data doesn't leave. You've got the latest data. It's very convenient. Now, again, we're not against exporting the data. We want to provide you with options. I'm just saying this is one of your options. And the cool thing I want to mention, actually, I'm going to skip over this. There's a lot of detail. It's in the slides, which you'll be able to download the slides later. But in one of our webinar demos, one of our starter kits, we have this method called in-graph machine learning for movie recommendation. It uses a classic, it builds on a classic collaborative filtering as well as content-based technique, because the different movies, different people like different movies, and basically we're trying to learn why they like them. But you see that this is a graph. The movies and the colors and the ratings that some people rated movies, and it forms a graph, and you can basically use a machine learning technique to take that graph data. Our example, it actually runs it inside TigerGraph, so you don't have to rely on any additional software. What I wanted to talk about here is the new in-graph machine learning techniques. You have neural networks, you have network embeddings. You may have heard about TigerGraph I'm in the process of co-authoring a book with O'Reilly about graph machine learning, and we talk about some of these techniques. So I'd love you to take a look at O'Reilly or TigerGraph. We'll talk more about Node2Vec and Deep Walk as random walk-based network embeddings. If you know some data science regarding natural language processing, you may have heard of word embeddings. And this is inspired by the same technique to do the same sort of predictive analysis and similarity detection with graph data. And on the neural network side, just in the very past 5 years, a lot of work has gone on with graph convolutional networks, graph recurrent networks, graph attention networks. People are seeing that you can actually use the graph. I told you before that you could ignore the edges during the training if you wanted to, but this is pointing out that, hey, let's keep the edges because they're valuable information. And so you can learn, you can get even more interesting. And sometimes one of the great things about this is they're showing that you can start with even smaller bits of training data. If you know supervised machine learning, you know one of the real challenges is having enough labeled tagged training data. And this is showing that if you have graph data, often you can start with a much smaller percentage of training data and still get good results. These next couple slides go through the basic architecture of how a graph convolutional technique works. This is just, a sketch of how deep learning works. You have your input layer, your output layer, and these hidden layers in between. And we just form these mesh of connections. And you start with random weights for these connections. And by repeating the process and using our labeled data, you learn weights for these connections. What the graph convolutional network does is it actually adds another step in each epoch. It says, we're going to take the graph, represent it as a so-called adjacency matrix, where adjacency matrix is where you make an n by n matrix, all the vertices. And if there's a connection between vertex 1 and vertex 2, then you put a value in that matrix cell for 1, 2. That's the adjacency matrix. If there's a connection, you put something in that cell connecting the two vertices. And so we basically just do a matrix multiplication by the adjacency matrix and just that little bit of information. So what you're convolving each vertex with its neighboring vertices. And there are more advanced techniques where it will learn weights for those neighbor connections. But the basic connection is you treat each neighbor equally. And that's the convolution. And that gives us a deeper insight. And so I've very quickly gone through these 3 techniques. I start off by saying, why graph? Then I talked about some techniques, but you got to have the right platform. Not every graph database is going to be the right one for this sort of modern analytics. First, you want to be able to handle large scale. You want a distributed database. You want it to have massively parallel processing. And TigerGraph even compresses the data, which gives you more efficient storage so you can get more bang for the buck, higher performance with the same hardware allocation. So you integrate all your data, it's automatically partitioned, and it's scalable and elastic. Secondly, you want to make sure that the compute is up to the task. You need to go wide and deep. So you want it to be designed as a native graph. TigerGraph is implemented in C++ for high performance, and you want to have the right storage architecture. So if it's designed right, you'll be able to do 5 or 10 hops in a single query with, again, many thousands of queries running per second. So that just because it's a graph structure does not necessarily mean it's going to be good for analytical workloads. So you want to, when you shop around, make sure you're getting that. And third, make sure that, again, that platform is designed for analytics. You need the scalability. You need to be able to traverse multiple levels. You need parallel processing. You even need the right query language, because not every query language is designed to write algorithms. Our G-SQL language is designed to write algorithms, and so you can do that analytical workloads. And lastly, for the democratization of analytics, for the citizen data scientist. We need to see a migration towards no code. There's unmet need for data scientists. We all know industries are hungry for more data scientists and machine learning experts. The market the vendors need to produce more no code solutions. And so TigerGraph is doing its part by providing no code visual query builder and no code data migration. So again, I mentioned graph is the natural model for connected data, provides richer data, and it's a natural model for machine learning, providing graph algorithms for unsupervised learning, graph features to make richer training data, and even new neural networks and graph embeddings, which fit automatically into the graph machine learning ecosystem. And graphs also can produce explainable AI, which is really key. So if you're interested in TigerGraph, just go to our website. We've got lots of starter kits, which are, you can try TigerGraph Cloud for free. And we've got 25 different application use cases to get you started. We have a developer portal at dev.tigergraph.com. Again, and you can go to learn.tigergraph.com to learn more about graph analytics in general and about TigerGraph. And thank you for your attention. This has really been great talking to you. Again, I'm Victor Lee. I'm head of product strategy at TigerGraph. And thank you. And I hope you enjoy the rest of the conference. I will be in the feed loop chat room to talk with you. Again, if any of you would like to chat with me further. Thank you.
Thank you so much, Victor. That was really enlightening and really interesting to learn about the applications that graph databases can bring us. We welcome our audience to participate with Victor in a Q&A. Simply put your question into the chat screen to the right of your screen, of your feed loop screen, and Victor's standing by to address any questions you have. And just to get started, I find it fascinating, the whole entity resolution challenge that you spoke about, the ability to, every company has this problem of multiple versions of their customer data, and one customer who may be working, maybe a customer of several different business units and have different accounts and data and everything else. That I find that fascinating, and that it's just something TigerGraph does a lot of work with customers.
Yes, we do a lot of this. Lots of our customers deal with this. Banks in particular are required by regulations to make a best effort at this, to find out who is the beneficial party behind an account. But just like I said, ordinary from medium-sized, large-sized businesses that may have users. Sometimes it's just somebody has changed their name due to marriage, or they used a nickname at one time, and then or they moved. So it's the same person, but they've just changed their information over time, and they don't go to bother. They forgot about their previous one, so the customer didn't merge them. Or there are different divisions of the same company, and so yeah, this is very common. They're finding that graph is a really handy technique for this, and it helps them make a more consolidated data set.
Again, I welcome everybody to participate in the Q&A. If you have a question for Victor, type it right in there. And of course, Victor will be available after the session in the networking chat room. So, either way, there's a chance to learn from Victor, learn more from Victor. Victor, what do you see what are some of the challenges that you've seen people encounter with implementing graph databases, and how they overcome those challenges? What are some things that you need to watch out for as you implement and move into this world?
Sure. There's a little bit of learning curve to understand what things graphs are good at, and so which type of tasks you really want your graph to focus on. It's not a replacement necessarily for some of their other databases. It may be in some cases. It really depends. There's always a little bit of work with tuning how you want to model your data, and then how you want to query. Just like with any technology, there are good ways to use it and not so good ways. And lastly, there's picking which of the many databases is right for you. Our emphasis is on scalability, on the property graph model, on real-time performance for both transactional or analytical workloads. There are other graph databases that may be better for semantic modeling, where people are the so-called knowledge graph. So there are different flavors of graph database. So it is worth spending a little bit of time to sort of learn about the different types.
Okay, one audience member here posts I guess a comment or a question. It looks like graph databases are a good way to catch streaming video traffic. For instance, such as Netflix, so people trying to catch people sharing accounts illegally. I don't know of anyone who does that. Do you know anyone who does something like that, sharing a Netflix account?
Oh, no. Yeah, but yeah. That I mean, and that's actually probably a pretty simple case, where because they have to be logged into a particular ID and they can sort of see the location. What I find interesting is where I prior to the pandemic, I used to travel for business quite a bit. And it used to be that you had to contact your credit card company and your bank card company to say, hey, I'm going to be traveling. So when you see that there are credit card charges in this other part of the world, that's me. Don't reject the transaction, Yeah. But now they're starting to, I've noticed that if I use the same credit card to buy the tickets or book the hotel, they've figured it out that that's me. And so they know that I'm traveling. And they also know my pattern. They know that Victor travels. And so they adjust the risk based on that. So Graph lets you model all that very, very sort of diverse information. You can kind of make all sorts of relationships to explain people's behavior in that way.
That's interesting stuff. And I could see, you've heard a lot about the TSA's no-fly list, for example, and a lot of people their names ending up in the no-fly list when they shouldn't be there, and all kinds of complications with that. I could see, very security conscious applications or agencies making good use of that technology as well.
Yeah, so there's the so-called problem of the false positive and the false negative. False positive is when, if they're trying to detect the blacklist people, the people on the no-fly list, and if they incorrectly identify you as somebody who should not be flying, that's a false positive. Different applications have a different tolerance for false positive versus false negative. And that's one of the big challenges in any sort of statistical analysis or machine learning in particular. And again, what we're finding is that we're not graph. Again, in the O'Reilly book that I'm working on, there's a chapter on talking about how graph is able to provide additional information so that you can increase the accuracy, so reduce the number of false positives and false negatives.
Okay, good stuff. And we look forward to the book. What will the title be?
It's called Graph-Powered Analytics and Machine Learning with TigerGraph.
Okay. And when's the release date? When can we expect it?
We're doing a sort of called early preview, a staged release. There are 2 chapters that are available now. If you go to the TigerGraph website, you'll probably see a big ad. You can get the first 2 chapters. They're actually not the first 2, they're the earliest 2, but we're actually giving you a preview of some of the later chapters that get into the more powerful use cases. I'm actually working on another chapter right now.
Okay, yeah, writing a book, that's still the old analog way of writing, of putting things together. But we look forward to seeing the book. Be sure to check out the first 2 chapters, as Victor pointed out, and That's going to wrap up our time. Victor's going to be over in the networking section. Just click on the left-hand side of your feed loop page there, and you can chat some more with Victor about graph databases and all kinds of good stuff like that. And Victor, thank you very much. This was a fabulous, fantastic presentation, and we enjoyed having you here with us today.